Second video on the Aspire compilation toolchain, we will have a look at the annotations and configuration. You may remember that the tool flow looks like this. We start from annotated source code. That code will be sent through a number of source-to-source rewriting steps that deploy some protections. The partially protected code will be compiled to object code, and then the code will be rewritten to eventually produce the protected program that consists of a client-side and some server-side logic to help protect the client. Now, two aspects will be discussed in this video. First, the annotations. We've chosen to use pragmas and attributes, like they are supported by GCC and LLVM and other compilers, to specify the protections that should be deployed on data and code in the program. Secondly, we have chosen for a whole tool flow that can be configured with one JSON configuration file. And in this video, we'll have a look at the pragmas and attributes, as well as to the JSON configuration file. First, part 1, the annotations. In this video, I will not discuss all the annotations, I will just give examples, but I can tell you that the whole syntax is formally defined using extended back-as-now form, and you can look it up in a public deliverable that's available on the project website. Now, in fact, we have two forms of annotations. A first form, which we call security requirement annotations, can be used to annotate your assets in your software and to specify the security requirements, like confidentiality, integrity, and so on. The second form are the concrete protection annotations, and those are the annotations that specify which protections should be deployed on which items in your code. It's the second form that we will look at in this video. The first form will be discussed and shown in the videos on the decision support systems. Now, I will not discuss all the protection annotations in detail, but let's have a look at some examples, and let's start with generic data obfuscations. And for those we use attributes. For example, if you want to specify that a variable x should be protected with XOR masking, you can add this Aspire attribute that says that the protection should be XOR masking and that the mask value should be the constant 12. In this case, it's a static mask. To specify that some variables should be merged and stored as one variable, you can annotate them as follows. You specify that the protection merge variables should be used. You specify which set each variable belongs to, such that the tool knows which variables to combine in which merged variable. And you can specify the width of the values that will occur and how they have to be merged into one variable. A third protection is static to procedural conversion. For example, suppose you have this sensitive string here that you want to remove from the program. Well, with this attribute you can specify that the data should be converted to procedure, and more specifically that you want a melee automaton, and then the protection tool will replace every occurrence of the static string by a function call to the automaton to generate the string on the fly. A specific form of data obfuscation is white box cryptography, where the goal is to hide keys that are used in a program. In this example, at the bottom you see a call to a decryption AES routine that has a ciphertext, a plain text, and a key as input. Now, to remove this key, you're going to annotate this function call, and you specify that it should be protected with white box crypto. You give this a label, I'll come back to that. You specify which crypto primitive should be implemented, and also the mode, and then that it is a decryption operation, not an encryption. Now, of course, this function call has arguments, and the tool needs to know the meaning of these arguments. They do not have to occur always in the same order. And for that, the variables that occur here have to be annotated with attributes. For example, for the cipher array here, we specify that it serves as a 16-byte input to a crypto routine that was labeled with xfix. And you see this label not just here, but you also see it here where we define the key, here where we define the output array, and here where we actually annotated the call to be replaced by a white box crypto primitive invocation. Another type of annotations we have is region-based annotations. In this case, we're going to mark well-structured code regions within functions, and we specify which protections should be deployed on them. For example, here we have a function and we have the function body, and we want to protect this in two ways. First, we want to deploy opaque predicates. So we mark the region with a begin and an end pragma, and we specify that obfuscation should be applied, and the ones that should be enabled are opaque predicates. In this case, we can also specify a parameter. This means that at every program point, with a 25% chance, an opaque predicate should be inserted. Now these regions can be nested, and we also specify that after opaque predicates have been inserted, this code should actually be translated to bytecode for interpretation with our soft VM. And so you see that we have nested regions. We also have a begin and end for the soft VM. This type of annotation with different parameters, we use it for many different protections like code mobility, anti-debugging. Now, in some cases, just marking one region is not enough. For example, for code guards, we need multiple regions. Yeah. Here, for example, suppose you have a decryption routine that needs to be guarded with a code guard. First thing we do is we label this as a guarded region. Again, with a begin and an end pragma. Then suppose that in some other function, we want to make sure that a guard is actually invoked on this first fragment. To specify where this guard should be invoked, we again annotate a region here in the decode frame function, and we specify that here an attestator should be added for the region called decryption. And you see this label occurring here, and also this attestator gets a label. In yet another function here, render frame, we can then specify that a verifier should be executed. We again use a label here. You see the label occurring here. And so what we'll specify here is that in this location in the program, a verification should happen of the result computed with the attestator that will be injected here. This way, a user of the code guards can make sure that the verification and the attestation are separated in time and in space, such that it's not easy for an attacker to link both and to circumvent the protection. For a remote attestation that runs in a separate thread, the annotations are slightly different. In this case, again, we mark regions, we have two here, that need to be attested, but in this case, we just need to specify how they need to be attested. We do not need to specify where that will happen, as it will just happen in a separate thread under control of a remote server. We can specify some features, however. For example, we can specify that the first region should be attested at startup, so before it's executed for the first time. Another option is to specify how frequent some code region needs to be attested, and then to specify some of the parameters of the attestations. For example, that a specific hash function should be used with specific forms of nonces and so on. Okay, this last annotation concludes the first part of the video. But as I mentioned at the beginning of the video, annotations are just one part to control the toolchain. The other part is a JSON configuration file. So here we have an example configuration file of our toolchain. In this case, is the configuration file for the DRM use case that we used extensively throughout the project. So we specify that it is an Android application that we want to compile. We specify all the plugins that we want to use in the toolchain, and so users can easily experiment with their own tools by replacing any of these standard tools by their own tools or by development versions or testing versions and so on. Then we specify the options for the different processing steps. The first processing step is of course collecting all the source code, so you see all the source files here. And actually before the source code in these files will be protected by the toolchain, you can ask the toolchain to apply some patches and to include additional annotations, and for that you can specify them here. For each step, you can also specify whether it should be just reversed, that means the files will be copied from the input of the pass to the output, or whether the processing step should be excluded altogether. Then in the order in which the processing steps are executed, you see the configurations. So for example, for Whitebox Crypto, you can specify some random seeds if you want to. We have a pre-processing step here. We have a data hiding step with a couple of options. We have a client-server code splitting step, which consists of multiple processes. For example, we use CodeServer to analyze the code, and then we have another plugin to transform the code. We have the extraction of annotations. In this case, you can also specify that additional annotations should be included in the program. This is such an extra annotation file. It's again a JSON file, and here you can specify additional annotations for complete functions. And you can use wildcards in those function names. For example, in this use case, we will link in code from our communication library. The functions in that library start with the prefix ACCL. And so we specify here that all of those functions need to be protected with a bunch of control flow obfuscations and with call stack checks. Now, going back to the main configuration file, we have additional source level processing steps. Then we come to the compiler phase. In this part, we specify first of all the options that should be fed to the preprocessor. After these preprocessing flags, you can also specify all the compilation options. You can specify if the communication logic needs to be included. This will be the case when you deploy online protections, what the IP address of the server will be. And then you can specify a whole bunch of linker options and the name of the library that you want to produce. It might also be a binary. Then we have a whole bunch of options for the binary rewriting part of the toolchain. For example, the toolchain can produce a self-profiling version of the unprotected application. Yeah? And the reason to do so is to collect profile information. Then the deployment of all protections can use the profile information to have a better balance between overhead and level of protection. Then we have steps for extracting native code fragments that will be translated to bytecode. We have bytecode generation step. We have a step in which the bytecode and a virtual machine to interpret the bytecode will be integrated into the binary or library to be protected. And then we have a phase where several more binary level protections are applied, and you can choose which ones you want to apply here. Furthermore, even on the protected application, we can generate a self-profiling version that will be able to collect dynamic metrics for evaluating the strength of the deployed protections on the software. Finally, we have two more sections. One is for server-side management. The toolchain can invoke a bunch of scripts that will prepare data for the server side of the online protections. So you can specify, for example, that data needs to be transferred to a specific server. And then scripts can be deployed for the different online protections to prepare the data and to set up the necessary tables in the server-side database, for example. You can also specify where the complexity metrics to evaluate protection strength need to be produced, and that's mostly it.